This is a short video lesson on the moment of inertia. Before we talk about moment of inertia, let's talk about just plain inertia. Inertia is a word that comes up in everyday language pretty regularly. You can talk about a company having tremendous inertia. That means it's been going the way that it's been going and it doesn't want to change. It's going to be difficult to change the way that company works, for example. Well, inertia in physics means the same thing. It means a resistance to change, but this time we're talking about motion. So in physics, inertia is a resistance to change in motion. Inertia typically comes up when we first start learning about forces and when we're talking about Newton's laws. Now, if we think about a change in motion, we remember that change in motion, that means acceleration. And acceleration, according to Newton's second law, is equal to a force applied divided by the mass of the object that the force is applied to. So the acceleration you get is proportional to the force. If I provide twice the force, then I get twice the acceleration, but it's inversely proportional to mass. If I double the mass, I only get half of the amount of acceleration. In this case, mass is an object's inertia. Mass is a measure of inertia. The more mass an object has, the more difficult it is to get it to change its motion. You have to apply more force to get the same acceleration if you're dealing with a large mass object. Moment of inertia applies in cases of rotation. So imagine that you've constructed something like what I've drawn here. This is like a barbell. There's a lightweight bar with two masses on the ends, and we can imagine trying to make it rotate here about this point in the center. Now this system is going to rotate differently than a system with the same mass but a different spacing between them. If you can imagine trying to twirl these objects, which one would be easier to twirl? If your intuition is telling you that it's the one with the masses closer together, that's absolutely right. This one on the bottom with the masses closely placed to the center of rotation is going to be easier to rotate. And if I wanted to stop rotating it, it'll be easier to stop this one. So the one on the bottom with the masses more closely positioned to the center of rotation is going to have less rotational inertia than the example at the top. This means it has a smaller moment of inertia. Moment of inertia measures an object's resistance to changes in rotational motion. And moment of inertia depends not only on the mass of the system, but where that mass is located. So there is a rotational form of Newton's second law. It tells us that the amount of angular acceleration that we expect to get out of a given amount of torque is inversely proportional to this symbol I, which is the moment of inertia, the resistance to change in rotational motion. So alpha is our angular acceleration. Torque is force applied in a way that produces rotation. So the amount of change in rotational motion depends on, of course, the amount of force you apply in a way that causes rotation, but the more resistant the resistance there is to a change in rotational motion, the less acceleration you'll actually get. So moment of inertia with the symbol I shows up in an equation. We need to know how to calculate it. So for an example of an object like a baton or the barbell I was talking about, there are really two masses involved. The bar that connects them is very lightweight, and we think about the center of motion. I'll mark that with a dot. In order to find the moment of inertia, we need to add up the products of the masses times their distance from the center of rotation squared. So here's how this is going to look. I'm going to take mass 1 out here. It's at a position of R1. So the product of mass 1 times R1 squared. Add to that, I have mass 2 over here and r2 is its distance from the center of rotation. So m2 r2 squared. This is going to be equal to I, or the moment of inertia. You could imagine creating a really complicated objects with lots of masses, all different distances. In that case, the general form for the moment of inertia is the sum of each mass, I'll give it an index number I, times that mass's distance from the center of rotation squared. And we just add it up for however many masses we actually have. If we imagine this bowling ball rolling down the alley towards the pins, it's definitely rotating. It may also be experiencing some torques, maybe friction with the floor, air resistance, things like that. The change in angular motion or angular acceleration is going to be inversely proportional to the ball's moment of inertia. And yet, the equation we had for finding moment of inertia involved adding up masses times their distance from the center of rotation. That's going to be a little tricky with a solid object like this. Where are the masses? It's really one big mass. We could consider little tiny pieces of mass and their distance from the center of rotation and add them all up. This is how we get to an integral. We can integrate little pieces of mass times their distance from the center of rotation squared. Well, if you're not doing calculus-based physics, you can always look these things up for regular solids. For example, the moment of inertia for a solid ball is equal to 2/5 the ball's mass times its radius squared for a rotation about an axis through the middle of the ball. For an object more like a basketball that's hollow in the middle, we actually get a different equation. So for the hollow ball, we are going to have 2/3 mr squared. The difference between these is that the mass is distributed differently in a solid object compared to a hollow object. So it turns out that if you apply the same torque to a hollow sphere and then to a solid sphere, you'll actually get different amounts of angular acceleration, different changes in rotational motion from that same torque, because the distribution of mass is different in the two objects. Moment of inertias add for a system of objects. In the real world, we often don't have simple balls or barbells with just two masses. Instead, we have more complicated objects. An example that I chose is this carousel. So to find the moment of inertia for this carousel, we would actually add up the various objects' moment of inertias. So the total moment of inertia here would equal the moment of inertia of the disk that everything is resting on. Add to that the moment of inertia of the canopy. Add to that the moment of inertia of the horses. And I do see that there's like a car on here too. This is a somewhat eclectic carousel. So the disk and the canopy, likely they would have moments of inertia that would be equal to 1/2 times the mass of the disk times the disk's radius squared. And then for the canopy, it would have a similar equation because it's a similar shape, like a disk. So the mass of the canopy times the radius of the canopy squared. And then for the horses, I would now add the sum of each horse's mass times its distance from the center of rotation squared. The reason that this would come up in a physics problem is, for example, a question about how much torque would we need to apply to get a certain angular acceleration on this carousel. To be able to do that, we would apply that rotational version of Kepler's second law, and we would need to find the total moment of inertia for this object. So just to recap some of the important points about moment of inertia is resistance to changes in rotational motion. To calculate moment of inertia for a system of point masses, moment of inertia, which has a symbol capital I, is equal to the sum of the product of each mass in the system times that mass's distance from the center of rotation squared. For a continuous mass distribution, to find the moment of inertia, we would need to integrate or look it up. And then finally, when we have a more complex system, which might include point masses and continuous mass distributions, the moments of inertia add together to create a total moment of inertia. Just like if you applied a force to two masses, you would add the mass together to get the total acceleration of the system. If we apply a torque to a system which contains multiple objects, we add the moments of inertia together, divide the torque by that total moment of inertia in order to find the angular acceleration of that system.